So I'm going to show you the results of the new observations of the transiting CoRoT-7, the smallest planet that CoRoT has found. And we observe it again with CoRoT during LRA06 run. So just I will start with some a small introduction to the system. CoRoT-7 was discovered in one of the first long runs of CoRoT in 2007. It has a short period of less than a day and a shallow depth that corresponds to 1.6 Earth radius. So this was the first transiting super-Earth discovered. The host star is very active and shows a 2% variation in the flux, and it also shows an induced radial velocity variations due to activity of 40 meters per second that is higher than the planetary signal. So this made difficult the estimation of the mass, and there were several techniques that were used to correct for the activity in the radial velocities that led to slightly different masses from 2 to 8 Earth masses. Also, in radial velocities, there are signatures for a second or a third planet in the system. So I show here the new light curve of CoRoT-7. And in the first 26 nights, there was simultaneous HARPS observations, 3 points per night. And the idea was to use the out-of-transit light curve, the CoRoT light curve, to correct the radial velocities using the FF prime method. And this was done by Raphael Haywood, and she obtained a mass for the planet B and C, but she couldn't confirm the existence of planet D. And the results were in AstroPH yesterday, so if you want to have a look at them, they are very interesting. We are very lucky in the second observations because the star seems to be in a lower activity state. And you see here a comparison between the old observations and the new observations, where the amplitude of the variability has decreased to almost half in the photometric flux. And also the spectroscopic activity index has decreased. And the activity signatures in the radial velocities has decreased to less than half. I will go back to the previous observations just to remind you of the results. And here I show a phase-folded 152 transits of CoRoT-7b in the previous LRA01 run. And you see that the best fit model is shown in red and gives us a transit-derived stellar density that is lower than expected, much lower than expected from spectroscopy. And you can see here the results of this fit. And the spectroscopic value is here in this, where it is pointed by the red arrow. And it's a 2 sigma, compatible at 2 sigma, but still worrying because normally a difference between the transit-derived density and the spectroscopic density is a signature for false positives. So this was tested by the authors that suggested that this was actually due to either stellar activity or TTVs that would create a V-shaped transit and not due to a blend. So to understand this better, we analyze separately the 2 runs of CoRoT. LRA01 and LRA06 are shown with red and blue. And you see here the shape parameters, the depth, the duration, and the inclination. And you see the results if we include the spectroscopic constraint in the fit are shown in green. And you see that besides the 2 observations don't agree with each other, none of them would give the result expected by spectroscopy. So we investigate what would cause this difference, and it could be the noise is too high in the light curve, just white noise or instrumental noise, or it could be a stellar activity. So we start by testing white noise, And to do this, we simulated transits at the timestamps of CoRoT for each of the runs and included noise levels corresponding to each run and analyzed them as the same as the real data. And you see here the results obtained for both runs. And we obtain a shape that is the same as we obtained for the new run. And this indicates that, and the real parameters are closer to here, around 80 degrees of inclination. And this indicates that the low signal to noise at the transit does not allow to constrain well the shape, and there's a degeneracy in the solution. So this explains the new observations, but not the shape of the first observations, the results in the first observations. So we tested instrumental noise by injecting transits in a star that is close by to CoRoT-7 in the previous run, and we obtained the same type of shape, characteristic of white noise, and that is different from what is observed in reality. So we then went to investigate stellar activity, and stellar activity could be a likely cause to affect more the previous run than the new run, since the star is now in a lower activity level. So as you've seen from Siller's talk, there's different ways stellar activity can affect your transits. If there are spots outside of transit, they will affect the depth, but in this case, because we only see a 2% variability, this only affected the derived density by 0.6%, so it's not enough. And another way is just by deforming the transit shape and making it difficult to normalize the light curve. So to test this, we injected transits. You see the transits here of CoRoT-7 are in red, and we injected transits at different phases, in this case here 0.6, to check if this could be the cause of the deformation of the transit probability distributions. And for 0.6, 0.4, 0.2, and 0.8, we obtained the same type of probability distributions, and they're all compatible with white noise, and none of them can explain what is observed for the first run. So another cause could be spot crossing events. And spot crossing events have been seen in several planets, as you heard today already. And here I show example in WASP-10, Kepler 17, and CoRoT2, and also a test of how they affect the parameter estimation here when a spot is at different latitudes in the star. And besides affecting the transit shape, they will also affect the transit times. So we investigated transit times. We cannot fit spots, the noise is too high, so we try by using the transit times as an indicator for these spot crossing events. And this has been seen in several systems that when there is spots, the transit times show a periodicity that is related to the rotation period of the star. CoRoT-8, Kepler 17, and WASP-10. So we calculated the transit times of CoRoT-7b, and here is the first run and the second run. And if you do a periodogram, we do see a peak at half of the rotation period of the star, and this hints that it's probably that some of the transits in the previous observation, $01, have been affected by these spot occultation events. So to try to not bias our estimation of the radius, we found a selection that is based in the out-of-transit flux. So if you divided the light curve in two halves and we analyze them separately, we see that the lower flux level shows shape that is V-shaped and as the whole light curve, but the higher flux level shows a shape that is in agreement with white noise and also in agreement with the results of Valerie 06. So we use this as our final, as just to reject the transits that would have been more affected by activity. So we use our selection with also all the data from the new run. We include the radial velocities that you've seen, all the radial velocities available, and the stellar tracks. And you see here the results of including the stellar tracks. The geometric model that I've been showing until now gives a big spread allowed density here. And as soon as you include the stellar tracks, you can constrain very well the solution and derive the planetary parameters. But this will be very dependent on the stellar parameters. And here we use the values from Brandt. And this was done with pastis that you heard from yesterday from Alexander, and was mostly done by Jose. So with the new value for the mass and radius, we have an estimate of the density of CoRoT-7, and I show here the mass radius diagram as you've seen before today and yesterday. And now CoRoT-7 has a density close to the Earth and is compatible with the Earth composition. And of course, if there's an atmosphere, there will be some digernacy in the solution. So to summarize, we found different results for the two CoRoT observations of CoRoT-7b. We show that the low signal to noise of the transits does not allow to constrain the shape of the transits well enough. And this leads to a digernacy, and we need an extra constraint coming from spectroscopy to be able to derive accurate system parameters. And also that in the previous observations in a higher activity level, there seems to be an extra noise component in the transit observations that we suggest could be due to spot occultation events. And then we used a selection on the out-of-transit flux to derive less biased estimation of the radius. But in this case, we found that the radius was not significantly affected by activity. And this could be due just to the strong constraint we are using on the stellar parameters that really constrain our final solution. Thank you.
Thank you. So we can take a few questions. So no question?
No. Just hypothetically, if you have these differences from two CoRoT runs on the same planet due to the activity of star, cannot you test this hypothesis, for example, taking a similarly low signal to noise Kepler planet and use different quarters of Kepler data and for an active host star, so you can check in a different data set